Hello folks, today I'm going to get an expression for the force between two current carrying conductors. So in the previous class what we did was we realized that there is an attractive force between two conductors in which current is flowing in the same direction, and there is repulsive force in those conductors in which current is carrying in reverse direction. So if I do like this, repulsive. If like this, it will be attractive. Now we have to go through the magnitude of the force there. So for that, let me draw the two conductors. So this time I am drawing the conductors in a different orientation. We have done two orientations in which one current was going like this or like this, either towards you or away from you. Next was I did like this, up or down, both up, both down, one up, one down, like this. So let me try one more orientation so that we can know that from every angle. So let's see that now the wires are going like this, So let's draw it. So this is the first wire in which current is going from left to right. So this is I1, this is I2, and its length is L1. Then we have next conductor. So this is shorter one, let us say. So it has current I2, and the length is L2. So length is L2. So let's go for the forces, the calculation of force. Let us say the distance between them is small r or even a. They write sometimes they write a, sometimes they write r. So the symbol is not much importance. The main thing is the concept. Now, first of all, the magnetic field due to this thing on this, the magnetic field strength or magnetic flux density because of this thing on this should be, let us do like this, it goes like this, it comes like this, so it should be in a direction like this. So this should be the direction of the magnetic field lines. So it is B12 because of 1 on 2, and its value will be, so from some theory which we call as Biot-Savart law. So and by using that law as well as some integrations, what we can have is the magnetic field due to a conductor wire, a straight conductor wire. So due to a straight conductor at some distance is equal to mu naught I divided 2 pi r. So you have to remember this thing. It is compulsory in different boards, but here in our case we just have to know this formula, and we would not need to know how it has come. So it comes with some integrations sort of things. So this is current flowing in the conductor, and this r is the distance of that point from the conductor where we are considering that magnetic field. And this mu naught is called as, a special quantity, universal constant, which is called as permeability. It is permeability of free space. Permeability of free space. It is related to the permittivity of free space as well as speed of light in vacuum. So from that connection also, people realize that magnetism and electricity are connected to each other, and the connection is with the velocity, speed of radiations, energy radiations in vacuum. So that's the connection that they found. Now the value of this B12 is equal to, let's write here, B12 should be equal to, from here it is mu naught I1 because of I1, then 2 pi into the distance is small r. The distance I have already expressed as small r. Now this will give it a force, and the force is Lorentz force. So magnetic field here, current into the right, and force should be here. So it is pulling force. This is F12, and the force should be equal to, F12 should be equal to BIL sine theta. Now what is theta? Theta is the angle between the conductor and the field line, direction of field lines. So conductor is like this, the field lines will be coming like this, so they come like this. So it's a whole circle. From this angle I can see a circle at like this. So it hits like this. Here it hits perpendicularly to this thing. So it comes like this. It perpendicularly hits like this. So theta is equal to 90 degrees. Now what is B? The B here is B12. What is I? The current flowing here is I2. So it is not I1. I1 is something others. And the length of this thing is equal to L2. So F12 is equal to B12 I2 L2 sin 90. And this B12 is equal to mu naught I1 by 2 pi R. Then I2 L2 sin 90 is 1. So our F12 is equal to something like this. So I can express it as, let me express it as, so F12 is equal to mu naught I1 I2 by 2 pi R, then L2, and this gives me F12 by L2 is equal to mu naught I1 I2 by 2 pi R. So the quantity at this left is called as force per unit length. Force per unit length experienced by the second conductor. So we have to take this into mind. So F12 is by L2 is this much and F12 equal to this much. Now let's go for its action on this. So the action will be current flowing like this, and here the magnetic field will be coming towards the observer or towards you. So this is the magnetic field. So this is B21 magnetic field. Now what will be the force? So magnetic field like this, current going there, so force will be down. So the force will be, this is F21. This will be the magnitude of force. So let's go for the magnetic field here also. So the magnetic field will be equal to, it is B21. B21 should be equal to mu naught, it's okay. So mu naught, it's okay. Mu naught. Then instead of I1 it should be I2 now, because this is the cause. Its effect on this we are seeing. So the cause is I2. It is I2 and then 2 pi R. Then what is the force on the conductor? So the force will be F21 is equal to, so magnetic fields, yeah, force F21, this will be equal to, it is B I L sine of again 90 degrees. It's because magnetic field coming like this. So from here it goes like this and like this, it comes like this and conductor. So the angle is 90. So what is B? B is, the cause here is B21. So it is B21, 21. The current here is I1, and the length here is L1. So B21 is equal to, let's write to the expression there. So it is mu naught I2 by 2 pi R I1 L1 sin 90 is 1. So this will be, so therefore F21 is equal to mu naught I1 I2 by 2 pi R, then L1, then so let me write here, it's of no use now. So I have need space for the formula for the relation. Then I will do like this. So F21 by L1 is equal to mu naught I1 I2 by 2 pi R. So we have two equations in which there is something similar. So here it is 1 and here it is 2. So by these two equations, what we can say is the force per unit length on each conductor is is equal. See, it depends on the product of the currents. It depends on the product of the currents, and it depends on the distance. So distance more, force per unit length less. Distance less, force per unit length more. Similarly, it is to the current as well. So that is, force per unit length is equal to mu naught I1 I2 by twice pi R. So this thing has been asked many times in the questions. They have asked whether they tell you to find the force per unit length, and they ask you whether they are equal or not, whether they follow third law or not. So of course, yes, force per unit length. So it depends on the product of the currents, and they're equal on both. Now, this equation has a significance that it has been used. It has been used to define 1 ampere current. At some point of history, this thing had been used to define 1 ampere current. So how did they do that? So mathematically they did that. So what they did was, let us say I1 is equal to I2 is equal to 1 ampere, and let R is equal to 1 meter. So that means we employ 1 ampere current in both wires, and they are placed at 1 meter. So if so, our F by L will be equal to mu naught into 1 by 2 pi into 1. So this mu naught is, its standard value in free space is 4 pi into 10 to the power minus 7 by this is 2 pi. So it will be 2 equal to 2 into 10 to the power minus 7 Newton. So 1 ampere current has been defined as such current which when allowed in two wires placed at 1 meter distance will produce a force of attraction or repulsion equal to this. So 1 ampere current means that amount of current which when allowed in two wires each of 1 meter length, two wires each at a distance of 1 meter will exert a force 2 into 10 to the power minus 7 Newton on each other, and they measure the amount of this force by the help of acceleration. They have it at rest, they allow current, and they allow one of them to move, or move. So by measuring the acceleration, by using very, very sensitive devices, they measure this force. So the very basic thing of current, which is the SI unit of ampere, so the unit of SI system in current has been measured in this way as well. Otherwise you would have to done like this. 1 ampere means 1 coulomb per second, and 1 coulomb charge means 6.25 into 10 to the power 18 electrons. So we'll have to count the electrons or do some complex mathematics, but here they have done it mechanically. So that is the significance of this chapter or this topic. So especially this numerical derivation of formula derivation of the force per unit length.